Mathematical sequences, why are they so important? And let's dive into a few special cases. First, let's look at the definition. So, a mathematical sequence is a list of numbers that follow a specific rule or pattern. So take a look below. We have 1, 3, 5, 7, and 9. What do they remind you of? They should look like the odd numbers to you. And the thing about the odd numbers is they go up in twos. So the difference between consecutive odd numbers is 2. Now, sequences are very important for real-life applications because the world around us is full of patterns, and sequences follow and measure patterns. So, for example, in finance, we have interest rates and mortgage rates. You have biology, DNA sequencing, and measuring the spread of diseases. You also have music and art. In music, you would measure things like rhythmic patterns, and art, you have color progressions. And finally, guys, just an example for you guys is computer programming. They actually like to use the Fibonacci sequence in dynamic programming. Now, let's look at some specific sequences. The first sequence I'm going to look at is one that students mostly learn first, and that is arithmetic sequences. And I'm going to look at the odd numbers, which we were saying before. An arithmetic sequence is a sequence where the consecutive terms go up or down by the same amount through addition or subtraction only. So you're just thinking about addition and subtraction. So here the odd numbers go up by a constant value 2. Now we call this the common difference. And this is literally just the first term. Let's derive a general formula for arithmetic sequences. So we have the first term, we like to call that A in mathematics. Think of it as the first letter of the alphabet. Now, in an arithmetic sequence, we are going to go up by the same amount. Now, remember I called it the common difference. So in maths, we like to say D. And I'm going to say plus D. Now, this value of D can be positive or negative. If D is positive, then the sequence is going up. If D is negative, then the sequence is going down. Now, let's use some algebra here. A plus D. So A plus D, we just write it as A plus D. We can't simplify it. Then the next term, we're going to add another D. A plus D plus another D. D plus D, so just using algebra here, I have D. I'm going to add another D, that is 2D. So it'll be A plus 2D. Can you see a pattern? Let's do one more. Add another D. 2D plus D would be 3D. So we have A plus 3D. Now remember, this is my first term. This is my second term, third term, fourth term. Can we write down a general formula for my sequence? And in maths, we call this the nth term. Nth term meaning, what if I wanted the 10th term? Now, when you look at each term, you can see that all of them have an A plus. So my nth term will definitely be A plus. But we now need to write down how many D's there are. So for the first term, there are 0 D's. Yeah, there's nothing there. For the second term, there is 1 D. For the third term, there is 2D. Fourth term, 3D. Can you see? For whichever term you are in the sequence, there is 1 less D. 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. So if I asked you guys about the 10th term, you would do 10 minus 1 and say 9D. So for the 10th term, it would say A plus 9D. So for the nth term, yeah, if this said N, I would do N minus 1 D. And this, guys, is the general formula for our arithmetic sequence. Take a look at this sequence. 1, 6, 11, 16, and 21. I want to find the 10th term. Remember my formula? First term plus 1 less than the term number times the common difference. So let's write down these things. What is the first term? Well, it's just the number 1. What is the common difference? Well, you can see to go from term to term, we're just adding 5. So D is 5. What is the 10th term? The 10th term is the first term, which is 1, plus 1 less than the term you're talking about. So the 10th term would be 1 less, which is 9, times the common difference, which is 5. 9 times 5 is 45, plus 1 is 46. Or the 100th term. And this is why it's important we learn these, because we're not going to keep adding 5 all the way up to the 100th term. Remember, it's the first term, 1, plus 1 less than the term number, which would be 99, times 5. 99 times 5 is 495, plus 1 is 496. These sequences on the board follow a specific pattern. They're made up of matchsticks. How many matchsticks would there be in pattern number 50? So I don't want you to draw it out. You'd be here for a long time. I just want to know how many matchsticks would you need in pattern 50? Well, we can see in the first pattern there is 4 matchsticks. Then we're adding 3 more, 7. Then we're adding 3 more. So here would be 10. Well, the first term here, A, is 4. And the common difference is 3. So we're just adding 3 each time. So in the 50th pattern, remember it's A plus n minus 1d. A is 4 plus the term number minus 1, which is 49, times 3. Now, 49 times 3. You can do 50 times 3, which is 150. For 49, you just subtract 3 from that, so that's 147. 4 plus 147 is 151. The next sequence I want to talk about is known as a geometric sequence. Now, a geometric sequence, kind of similar to an arithmetic, is where the terms go up by what we call a common multiplier or a common ratio, implying multiplication or division, but division is just the reciprocal of multiplication. Now, in this case, we're doubling each term. Now, when you're going up by a common multiplier, we can also call this exponential growth. And to emphasize how powerful exponential growth is, I want to tell you guys about a legendary story that originates in India, known as the wheat and the chessboard problem. A long time ago, a very smart man named Sessa presented the king at the time with a very unique invention, and that was the chessboard. The king was so impressed by the invention that Sessa had presented to him, he granted him any reward. And so Sessa, being the very smart man that he is, said, "All right, king, I want you to give me 1 grain of rice per square and double it every consecutive square." So the first square, Sessa would have 1 grain of rice, the second square, 2 grains of rice, 4 grains of rice, etc. Now the king, maybe not being nearly as smart as Sessa, said, "No problem, I can grant you that wish." Little did he know, that amounts to 18.4 quintillion grains of rice, which, guys, if you were to pile that much rice, would be larger than Mount Everest, which is crazy. This is more grains of rice than is produced over decades of farming. And that is the power of geometric sequences. The last sequence I want to talk about is the Fibonacci sequence, which is really important. To find the next term in a Fibonacci sequence is you add the previous 2 terms starting with 1, 1. So 1 plus 1 is 2, 1 plus 2 is 3, 2 and 3 is 5, etc. The Fibonacci sequence relates to something known as the golden spiral, which relates to many things in real life. Weather patterns, seashells, plants. The human body actually has proportions which follow something close to the golden ratio, which we're going to talk about later. Also in architecture. Now, let's build this golden spiral using the numbers of the Fibonacci sequence by drawing squares of side lengths that follow the Fibonacci sequence. So first I'm going to start off with a side length of 1, first one, and also another one of side length 1. Now that means I can draw a square of side length 2 because 1 plus 1 is 2. So up here I have a square of side length 2. I can then draw a side length 3 square because 2 plus 1 is 3. Then down here I have 3 plus 1 which gives me 5. So down here I can have a square of side length 5. Next we can do a square of side length 8, 5 plus 1 plus 2. So going from here, 8. And then finally we can do 13. Now this is going to be quite a large square. I'm actually going to enclose all of these numbers, or nearly all of them, over here because we have 3 plus 2 plus 8. Now let's draw the golden spiral. To do that, we go from corner to corner like this. So go round, corner, to corner, like that. Having spoken about the golden spiral, you're probably wondering about this golden ratio. Now, the golden ratio is this figure, and it goes on forever. When you divide consecutive terms, you get numbers that progressively get closer to the golden ratio. For example, 1 divided by 1 is 1. Then we have 2 divided by 1 is 2. 3 divided by 2 is 1.5. Then we get 5 divided by 3. Well, this is 1.6 recurring. Then we have 8 divided by 5, which is 1.6. Then finally, I'm going to do 13 divided by 8, 1.625. To demonstrate that it does progressively get closer, is 610 and 377 are consecutive terms in the Fibonacci sequence just much further away. 610 divided by 377 is 1.618037, which is much closer to the golden ratio than the other numbers that I showed you guys. And that, guys, is a wrap. I've shown you why sequences are really fundamental to our studies and how they relate to real life. Also showing you some really important sequences. Guys, if you like this video, I'd really appreciate if you hit the thumbs up. And in the name of our favorite person, Sessa, and the chessboard, I want you to comment Royce down in the comments and subscribe for more content like this.